So we have a new chapter on oscillation. Now this is a second last chapter in our course. Okay, so we still have two chapters to go. The first chapter is oscillation, and the other chapter is waves. First, we talk about a simple harmonic oscillation. This is abbreviated as SHM. Now, suppose you have a top view of a spring mass system. A spring mass system means a block, a massive object is attached to a spring, and the other side of the spring is attached to a fixed end. So you now have a top view of this. So imagine now the block is advanced on a smooth horizontal table. So there's no frictional force, but under the action of the spring, the block will oscillate. Okay, and it's oscillating horizontally, so we don't have an effect of gravity. So we don't need to consider gravity because we are looking at from the top, and the oscillation is in the horizontal direction. So initially, if we stretch the spring such that the block, the spring is at a distance a from the equilibrium position. Okay, now we imagine that the x equal to 0 is the equilibrium position. That is the unstretched position of the spring. Now we stretch the spring by a displacement a, and we release the block from rest. So what will happen according to our intuition? The spring will exert a force on the block, right? It will push the block backwards. So the block will accelerate in the backward direction, and that is to the negative x direction. It will accelerate in the negative x direction. Now, what would happen when it reaches the equilibrium position? Will it stop here? No, because the potential energy that is stored in the spring has now converted to the kinetic energy. Because the potential energy at the equilibrium position is 0, right? So initially, the spring stores some equilibrium potential energy, and when the potential energy becomes 0, all the energy is converted to kinetic energy. So the block now carries a certain kinetic energy, which is in the negative x direction. So the block will overshoot the equilibrium position. It will go to the negative x direction with a velocity. Okay, and what happens is that when it compresses the spring to a certain degree, in fact the same amplitude a, the block will be stopped. Okay, because when it overshoots the equilibrium position, it actually compressing the spring. When it compresses the spring, the kinetic energy will go to the potential energy again. So eventually, when all the kinetic energy change back to potential energy, the block will stop momentarily. And what will happen next? There is a pushing force instead of a pulling force, right? Because the spring is now compressed. So there's a pushing force that pushes the block backwards. And it overshoots the equilibrium position. Eventually, it goes back to its original position of release. And that completes the cycle. And if there's no energy loss, this cycle will repeat again and again and result in oscillations. Okay, oscillations means moving back and forth with cycles that is repeating itself. Okay, now what is a curve that describes such a motion? If we plot a graph of x versus time, then we'll probably we use a smooth curve to join all the points here. Then probably we will end up with something like this. And obviously, there's a kind of curve that best describes the motion, and that is a cosine curve. A cosine curve initially has a maximum value, and it goes to 0 at the angle equal to pi over 2, and it goes to negative minimum as angle pi, and again it goes back in a full cycle of 2 pi. Okay, so that's a cosine curve. Now, so a particular solution to that problem, we call a particular solution because it does not exhaust all the initial condition. We only assume the block release from rest. We do not assume any initial velocity on the block. So that solution is not general. It corresponds only to a particular initial condition in which the block is at rest. So for that case, we have a so-called particular solution, and that solution is described by A cosine omega naught t. A is the initial amplitude of the oscillation, and omega naught is a constant called the angular velocity. Okay, now this angular velocity is actually the angular velocity you learn in circular motion. Okay, it's the same concept of angular velocity. So if you plot x against t, you end up with this curve, the red curve, right? And the curve repeats itself in a period of time, in a time of equal to the period. And we denote the period by capital T. After a time t, the curve repeats itself. Okay, and the maximum amplitude of the oscillation is called A. That is called the amplitude. That is the maximum oscillation. Okay. So how is the frequency related to the period? How is the angular frequency related to the period? Now, the cosine curve repeats itself when the argument of a cosine, when omega naught t goes from 0 to 2 pi. So that means when the argument called omega naught t goes from 0 to 2 pi, the function will goes back to itself, and that is of course a period. So that corresponding to t goes from 0 to the period t, capital T. Okay, so that means omega naught capital T is equal to 1 cycle of the cosine function, and that is 2 pi. And so we have the period t equal to 2 pi over omega naught. So that is the relationship between the period and the angular velocity. Now we have mentioned it a few times before. This is an important relationship. I hope every of you will remember it. Now we only handle the case for a 0 initial speed. We will come to a general case later. The general solution will involve not only the cosine term but also the sine term. Okay, we will come to the general solution in a few slides later. Now, but we want to derive it. How to derive that equation of motion for an oscillating mass. Now we suppose the equilibrium position is the unstretched position of the spring, and we call that position x equal to 0. Now, if the spring is now stretched, if the spring extends by a distance x, by a displacement x, then that would be a restoring force from the spring. The restoring force has a property that the magnitude of the force is proportional to the extension. So the spring extends more, the larger the force. Okay, so the force is proportional to the extension. So F is proportional to x, and the proportional constant is called K. K is called the spring constant. It's constant. It's a constant that characterizes the spring. Okay, for a specific spring, the K is a constant. Now, but the force and the displacement are in opposite direction. If we stretch the spring, if we extend the spring, the force will be pulling me back, right? If we compress the spring, the force will be pushing me back, right? So the force is always in opposite direction to the displacement. And that's why there's a minus sign here. So F is equal to minus Kx. That is the net force acting on the mass now. So we use Newton's second law, F equal to ma. And ma is, of course, the mass times the acceleration, d squared x dt squared. And it's equal to the net force. Ma is equal to the net force. In this case, is minus Kx. Now we define the angular velocity or the angular frequency by square root K over m. We define omega naught as square root K over m. Okay. Now, why do we define like this? Because we know that after such a definition, the equation of motion will become something like this. We divide the whole equation with the mass m, and K over m is omega naught square. So we have d squared x dt squared equal to minus omega square naught x. And that is the standard equation for simple harmonic oscillation. Okay. Now, what is the meaning of this equation? The meaning of this equation is that we want to find a x, a certain function, x as a function of time, such that after two differentiation of x with respect to time, it will goes back to x itself, but with a negative constant in front. the negative constant is given by minus omega naught square. We want to find such a function. Now, which function will give such a result after two differentiation? We can think about sine and cosine. When we learned about sine and cosine at the beginning of this course, we mentioned that sine and cosine have some very special property that after two differentiation, it goes back to itself, but with a negative sign. So that property will make it very suitable for solving this equation. Okay. Now suppose we start with a cosine omega naught t. If I differentiate once, it becomes minus sine, and because of a chain rule, it comes out a constant omega naught comes out, right? And if I differentiate once more, the sign will become a cosine. Again, another factor of omega naught coming out. So totally we have two factor of omega naught, that is omega naught square. So now a cosine after two differentiation, it becomes cosine again, but with the constant minus omega naught square in front. Again, if we start with a sine, after two differentiation, we still go back to the sine. But again, we have that constant minus omega naught square coming out. So of course, you can see both the cosine function and the sine function, which take this form, satisfy this equation. If you differentiate twice, it goes back to itself, but with the constant, with the addition additive constant minus omega naught square. So it satisfies this equation. So we found two solutions. The two solutions are given by cosine omega naught t and sine omega naught t. Okay, and we claim that, we claim that if we denote the cosine by x1 and the sine by x2, we claim that the general solution to that differential equation is a so-called linear combination of the two solutions. Okay, we use a constant c multiplied by x1 and another constant d multiplied by x2, and we sum the two solutions up. And we call this the general solution x. We claim that this solution x also satisfies the equation. Now, how do we know that? Now, that can be proven by a simple substitution. We substitute this x into the equation. We find the second derivative of it. Now, of course, the second derivative will act on each of this function, right? Because the differential operator is linear, so it acts on each of the functions. So I have a c multiplied by a second derivative of x1 plus d multiplied by a second derivative of x2. But since x1 and x2 are both the solution to the differential equation, the second derivative of x1 or x2 will give you back x1 and x2, but with a constant minus omega naught square in front. So it goes back like this. Okay. Second derivative of x1 become minus omega naught square x1. Second derivative of x2 become minus omega naught square x2. Now we extract the constant omega naught square out. And the quantity inside the square bracket is cx1 plus dx2, which is exactly x. So it becomes minus omega naught square x. Okay, so obviously x, which is a linear combination of x1 and x2, also satisfies the equation. Okay, now this property will hold because the equation of linear. What is meant by a linear equation? The linear equation means x and its derivative appear only once in a term. You don't have term that goes at x squared or dx dt squared or x times dx dt. You don't have that. For example, on the right-hand side of this equation, you only have a derivative of the second derivative of x only, but not multiplying any of the other form of x. And also on the right-hand side, you only have an x, a single x on the right-hand side. You don't have a term with x squared or x cubed or x to the power 5, etc. And this kind of equation is called linear equation. Linear equation has such a property. If the solution x1 and x2 are the solution to this equation, then the linear combination of x1 and x2 is also a solution. That is the property for the for the linear equation. Okay, if you don't believe it, you can prove it in general. If x appear only once in a term, then the linear combination of the solution is also a solution. Okay. Now, so the general solution is given in this form, and we use this constant C and D goes before the cosine and the cosine term. You add them up together. Now, C and why are there two initial conditions? Because where are there two constants? Because we have two initial conditions for this problem. The first initial condition is, of course, the initial position, where the motion starts. Initially, where is the block, right? But there's also another condition. The condition is with what velocity does the spot start its motion? The initial velocity also matter, right? So we have two initial conditions, the initial position and the initial velocity determining the whole motion. So that two pieces of information exactly determine these two constants C and D. Okay, so that's why we have two constants. Okay. And mathematically, the two constants come from the integration of a second order differential equation. Because a second order differential equation involves the second derivative of x with respect to t. So you need to integrate the equation twice to go back to x, right? When you integrate once, you got an undetermined constant. You integrate twice, you got two undetermined constants. And so that's why you have two constants now. And physically, that corresponds to the two initial condition, initial position and initial velocity of the object. Now we can have another form of the initial condition. Instead of writing it as C and D, we can also write the solution in terms of the amplitude of oscillation and the phase. Now, how do we do that? We draw such a right angle triangle. With C on the base is equal to C, and D is equal to the vertical side. Okay. Now, if we assume this angle to be fine, then the hypotenuse, because the vertical side is D, the horizontal side is C, the hypotenuse, I call it A, will be equal to C squared plus D squared. Is that right? C squared plus D squared square root by Pythagoras theorem. Is that right? And I can also express D in terms of A and phi. If this is A and this angle is phi, then D is A sine phi. And the base C is equal to A cosine phi. Now we simply remove the constant C and D. We use another two constants to replace that. And those two constants is A and phi. Now everything expressed both in terms of C and D can also be expressed in terms of A and phi. That is our idea. Okay. Now, so without loss of generosity, we assume this to be a minus sign because we can have D negative anyway. So without loss of generosity, we take this as a minus sign. Now, if we take this as a minus sign, then C is equal to A cosine phi, right? So I have cosine phi cosine omega naught t as the first term. And D is equal to A sine phi. So I have sine omega naught t sine phi as a second term. And there's a minus sign in between. And A is simply square root C squared plus D squared, right? This is A. Okay. Now you see this combination, cosine omega naught cosine phi minus sine omega naught sine phi can be written as what? Can be written as a combined angle. Okay, can be written as cosine omega naught t plus phi. Okay, this is a standard formula. If you don't remember it, you go back to your high school textbook and look at this formula. I suggest you remember it. Okay. Now, so we, instead of writing it in the solution in terms of C and D, we now write the solution in terms of A and phi. We still have two undetermined constants. Now, so the two forms of the solution are equivalent to each other. You either express it in terms of the constant C and D, or you express it in terms of the constant A and phi. Now, why do we want to express it in this way? Because A is actually amplitude, right? You see the cosine here. So the cosine function is still there. So the A will become the amplitude. And the phi is the initial phase. The phi determine the shape of the cosine curve at the beginning of time, t equal to 0. So this is just an alternative form of expressing the same solution. Okay, now you can use either form to match the initial condition. Okay, now let's try some of this initial condition and you'll see how to match those conditions. But before going further, I would like to talk a little bit more about this phase factor phi. Okay, now if phi is equal to 0, then this is simply a cosine curve. The cosine curve looks something like this, right? This is a simple cosine curve with phi equal to 0. The amplitude is obviously A, and this is the period. The period is the time for the curve to repeat itself. So when you go from first peak to the 0 point here, I have a quarter of a period, right? Okay, so this is how a cosine curve looks like. Now suppose we now add the phi. Suppose phi is not 0. Now, initially, we have, if phi is 0, then we have the first peak located at t equal to 0. But with phi not equal to 0, the position of the first peak has changed. The function is still a cosine function, but there's a shift in the whole curve. And that makes the first peak change its position. So how do we find the peak, the first peak? Well, the first peak is always given by the argument of the cosine being 0, because when the argument when the thing inside the bracket is 0, the cosine is a maximum. So the maximum or the first peak always corresponding to omega naught t minus phi equal to 0, and this equation will give me t equal to minus phi over omega naught. If you like, you can write omega naught in terms of the period t. And that gives you minus phi over 2 pi t. Now, how do I interpret this this form of the equation? Now you can see the first peak has, if I assume phi is positive, then you can see the first peak, the position of the first peak, that is t, is shifted to the negative t side by this amount, right? So you imagine if phi is, if I assume phi is positive in this diagram, then the whole curve will be shifted to the negative t side by amount of phi over 2 pi t. Okay, so a positive phi corresponding to a shift in the whole curve to the negative side. If phi is negative, then the whole curve will be shifted to the positive x side by the same amount. Okay, so that is the idea of the phase. Okay, now how to interpret this phase? It may be instructive to look at some common angle. Now suppose phi is equal to pi over 2. If I put pi over 2 here, then it becomes 1 over 4, right? It becomes a quarter. It becomes a quarter of a period. So that means an angle, a phase angle of pi over 2 corresponding to a quarter of a period. And that is something you should remember because you always switch between the angle and how many periods that the curve has shift. So a shift in the angle, in the phase angle of pi over 2 corresponding to a quarter of a period. How about pi? If phi is equal to pi, then this becomes half of period. So shifting the angle by pi corresponding to shifting the cosine curve by half of the period. So the maximum will become the minimum. Imagine you shift the cosine curve by half of the period, and then you shift the minimum point to the maximum point and vice versa. Okay? And if phi is equal to 2 pi, you shift the whole curve by 1 period. Okay? So these are the common angle and the corresponding a period that you may need to remember. Okay, because when we learn about wave, this phase angle actually appear very frequently. So it's better for us to get used to it and understand its meaning. Okay, when phi is present, then it corresponds to a shift of the initial position of the curve either to the positive x or negative x side. Now let's take a look. Also take a look at the velocity curve and acceleration curve. For simplicity, we ignore the phase angle. Okay, we put the phase angle phi to be 0, and we look at the particular solution a cosine omega naught t. If I differentiate it to get the velocity, I will have omega naught a sine omega naught t, right? Cosine become a minus sign, and we take out a factor of omega naught. Okay, we differentiate again to get the acceleration, and the sine become a cosine again, with 2 omega naught coming out, so we can become minus omega naught square a cosine omega naught t. But I noticed that this a cosine omega naught t is simply x, so the acceleration become minus omega naught square x. Now this is nothing but the original differential equation. A is just d square x dt square, right? And right hand side is minus omega naught square x. So it's just the original differential equation. But writing the equation in this form allow us to see very clearly the relationship between the acceleration and x. You can see the acceleration is actually proportional to the displacement. Okay, a is proportional to x, but they are always in opposite direction because of this minus sign. You stretch the spring to this side, the acceleration, the net force will be pulling it back. Okay, so that's why the acceleration or the net force is always in opposite direction to the displacement and is proportional to the displacement. Okay, now this is actually a typical property for SHM, for simple harmonic motion. If you see the equation of motion to be in this form, the acceleration being proportional to x with a minus sign, then that means the motion is a simple harmonic oscillation. There's no other motion with such an equation. Okay, so that is a characteristic equation of motion for simple harmonic motion. Now let's look at the phase angle. Okay, the cosine curve looks like this, of course. How does a minus sine curve looks like? A minus sine curve will look like this, right? You have a sine curve first, then the minus sign will flip it up and down, upside down. Okay, so you have a minus sine curve looks like this. Now, if you examine these two curves, you will find that the velocity curve is simply the displacement curve shifted to the negative x direction by a quarter of a period. If you imagine this curve shifted towards the negative x direction by a quarter of a period, you produce the velocity curve. Is that right? Now, how about the acceleration? The acceleration goes as minus cosine omega naught square. So it becomes something like this. The maximum of the cosine become minimum, right? And that again corresponding to a shift of the velocity curve to the left side, again by a quarter of the period. So differentiating once on the cosine curve or the sine curve will shift the curve by a quarter of a period to the left, to the negative t side. That is something probably you may like to remember. So differentiating a cosine curve or sine curve will shift the curve by a quarter of a period to the left. Okay. Now, but of course, although the phase is related like this, the amplitude because the x and v and a, they are different quantities, so the amplitude is of course different. The maximum value of the displacement is of course the amplitude a, but the amplitude for the velocity is omega naught a. Okay, and the amplitude of the acceleration is omega naught square a. Okay, is that clear? A is the displacement, maximum displacement, which we call the amplitude. The amplitude, the largest value for the velocity is a multiplied by omega naught. Omega naught carries a dimension per second. So distance per second will be the velocity. So dimension is correct. If you multiply 2 omega naught, that turns the displacement into the acceleration. Okay, and the maximum acceleration is omega naught square a. Okay. Now we can talk about the energy. In order to calculate the mechanical energy of the system, we have to know the velocity and the displacement, but both we know, right? Already calculate. The displacement goes as cosine function. The velocity goes as a minus sine function. So the potential energy of the spring is half kx squared. So we simply substitute this, the cosine function as the x term. So that become half ka squared cosine squared omega naught t. The kinetic energy is half mv squared, but v is given by this, right? So the kinetic energy is half m omega naught squared a squared sine squared omega naught t. Now, but when we look at the kinetic energy coefficient carefully, we find that m omega naught squared is actually k. Why? Because omega naught is by definition k over m square root. So omega naught squared is actually k over m. And when I multiply by another m, the m cancel. And so the combination m omega naught squared is simply k. So both the potential energy and the kinetic energy, they have the same coefficient in front. And that coefficient is equal to half k squared. But one goes as a cosine square and the other term goes as a sine square. The potential energy varies as cosine square. The cosine square function looks like this. Okay, this is a cosine square function. Now it never goes below 0 because cosine square is always positive. So it varies between 1 to 0 like this. And the period of a cosine square curve is actually half the period of a cosine. Now this is a period of a cosine. Okay, but if you have a square, then you can see this curve varies like this. So the cosine square actually have a period that is half of the original period of the cosine function. Okay, and this is a sine curve, the sine square curve. The red curve is a sine square curve. Okay, so the U curve, the potential energy curve goes like the blue dot line, and the kinetic energy curve goes like the red solid line. And when I sum them up, cosine square plus sine square by identity, by the trigonometric identity is equal to 1. So the total energy is half k squared, which is a constant. And this has to be true because the system is not subjected to any friction or dissipated loss. So the total mechanical energy is always conserved. The kinetic energy plus the potential energy is equal to constant. So that only reflects the conservation of mechanical energy. Okay, so you have a cosine curve like this, cosine square curve like this, and sine square curve like this. They add up to a constant curve, and the constant value is half k squared. Okay. Now let's talk about how to match the initial condition. We emphasize there are two initial conditions. At time 0, the initial position is x naught. And suppose at time 0, the velocity is also known, and the initial velocity is called v naught. We are going to match the constant c and d with these two initial conditions. So how are we going to do that? Now we know in general, the displacement can be written as a linear combination of cosine term and the sine term. C cosine omega naught t plus d sine omega naught t. And the velocity is simplified by a differentiation. So we differentiate the cosine, it becomes minus sine. We differentiate the sine, it becomes a cosine. And do not forget, you have another factor of omega naught coming out. Now, so we mesh the initial condition. The initial position can be found by putting t equal to 0 in this equation. And sine 0 is of course 0. Okay, when t is 0, sine 0 is 0. When t is 0, cosine omega naught t is 1. Okay, because cosine function is largest at 0 argument. So only the cosine term remains, and the cosine is 1. So we only have C. So that means C is equal to x naught, the initial position. And how about the velocity? The initial velocity is simply given by putting t equal to 0 in this equation. Is that right? For this equation, the reverse thing happened. The sine term vanish because sine 0 is 0. The cosine term remain, and cosine 0 is 1. So what remains is omega naught d. Okay. And I have the initial velocity v naught, so omega naught d is equal to v naught. And that means d is equal to v naught over omega naught. So we now have the correct solution. The correct solution with this initial condition can be written as x naught, which is c, cosine omega naught t, plus v naught over omega naught, which is d, sine omega naught t. So this is the general solution. Okay, we already encompassed all the initial condition. If you have an arbitrary initial condition with some x initial position and some initial velocity, you put these two into this equation, you got the general solution. Okay. Now we can also express, instead of the initial condition in terms of C and D, we may also use this solution and express the initial condition in terms of A and phi. Okay, but how do we match the initial condition? Now, I prefer to leave it to you as an exercise. Please differentiate the x to find the velocity. And then by setting t equal to 0 in x and t, you got, for the initial position, you got x naught. For the initial velocity v naught, you will be arriving at two equations that relates x naught, v naught to A and phi. And let's think about how to solve that two equation to find out A and phi. So let's write down the two equations first. I'll give you 3 minutes to write down the two equations. And if you know how to solve it, please let me know you know how to solve it. Hey, you got the answer? Somebody answer me. I think you are correct with A, but I'm not that sure for the angle phi. There seems to be a simple expression for phi. For another student, I think you got for Mr. Chen, I think you got the correct expression for A. Now maybe let's do it together. Okay. Let's do it together. Sorry. Now this is our problem. The initial position is not, and the initial velocity is v naught, and we are going to match this with the solution a cosine omega naught t plus phi. Okay. Now v is what? V is simply the differentiation of x, and the cosine become minus sine, right? And we also have a factor of omega naught coming out. So that is the answer for the velocity. Now, when t is zero, we don't have this term, right? So x0 at time 0 is equal to a. We simply don't have this term, so we have cosine phi only, and that is equal to x naught. And when we put t equal to 0 in v, we don't have this term, and it becomes sine phi. So the v0 is minus omega naught sine phi, and that is equal to minus v naught. Is that right? Now there's a simple way. Sorry, I missed a factor of a here. Now there's a simple way to eliminate phi. Okay, because we know that cosine square phi plus sine square phi is equal to 1. Is that right? That's a trigonometric identity. So that means x naught over a square, which is cosine square, plus v naught over omega naught a square is equal to 1. Okay, it is simply cosine square. This is simply sine square. And so we got a now. We move the a to the left-hand side and we take the square root. A will then become x naught square plus v naught over omega naught square square root. Now we can take the a by definition positive because we can use the phi to adjust whether this quantity is positive or negative anyway. So we leave the negative sign to negative positive sign to phi, but not to a. We define a to be positive. Okay. Now how can we find how can we find out the angle? Now we can eliminate a by dividing the second equation by the first equation. Is that right? When we divide the equation, we simply get rid of a. And sine phi over cosine phi is what? Sine phi cosine phi is simply tangent, right? And that means minus omega naught tangent is equal to v naught over x naught. Is that right? So that means the phi is equal to r tangent minus with a minus sign here, v naught over omega naught x naught. So that is our answer. Okay. So I shared with you all. Okay. So you review it when you have time. Sorry. Any problem so far? If no, then we proceed a bit forward. Now this is a simple pendulum problem. We met in our first problem set, right? In problem set, we are told to use dimensional analysis to find the period of a simple pendulum when it has a small amplitude. Now we are going to derive it more rigorously now because we know the equation for simple harmonic motion. Now we know the Newton's second law for rotation, so we're going to use that. The Newton's second law of rotation says the torque acting on a body is equal to the rate of change of angular momentum. This is the net torque. The net torque acting on the body is equal to its rate of change of angular momentum, dl dt. Now, how do we calculate the torque of a pendulum? If this is a bob of mass m and it is hinged, it is tied by a string of length L to a fixed point. And the string now makes an angle theta with the vertical. So what is the torque acting on this bob about the fixed point? Now it's easy to calculate. We can notice that the weight is vertically downwards, right? So weight is mg, and the line of action of the weights, it at a distance, the distance of the line of action from the pivot point, from the point O here, the fixed point here, is L sine theta. Now this is a line of action, right? The force act along this line, right? This is the weight mg, the force act on this line. And this distance, the distance between the line of action and the fixed point is this distance. And this distance is equal to L sine theta. Is that right? Because it's L, this length is L sine theta. So the torque is equal to mg multiplied by L sine theta. I net the negative sign here because the direction of the torque tends to decrease the angle theta. Does it make sense? The angle increase in the anti-clockwise direction, but the torque actually is in the clockwise direction. So it tends to decrease the angle theta. And to account for this, we have to add the negative sign. If we take the increasing direction of the angle to be positive, then the torque will be in the negative direction. And that is with a negative sign, okay? Now the torque is there. How about the change in angular momentum? The angular momentum of this particle, of this bob, because it's undergoing a circular motion, so the linear velocity is simply v equal to L omega, where L is the length of suspension, essentially the radius of the circle, multiplied by the angular speed omega. Okay, so the angular momentum is mvl, but v is L omega, so that becomes ml squared omega. We replace the v with L omega, and we express the angular momentum in terms of omega, and so that's ml squared omega. But omega is the rate of change of angular velocity, angular position. Omega is the angular speed, angular velocity, so it's equal to d theta dt. Okay, so we have this formula. Now differentiating the L with respect to time means I differentiate this once more. And so I got d squared theta dt squared for the right-hand side. Okay, the left-hand side is the torque. The torque is given by this. I just copied it down. So it becomes minus mgl sine theta. Now we arrange this equation a little bit to make all the constant on the right-hand side. So d squared theta dt squared is equal to minus g over L sine theta. Now this equation is rather difficult to solve. it has an analytical solution, but I don't want to solve it at this level because it involves a complicated function known as elliptical function, which you do not know. So I don't prefer to solve it analytically, and I will leave it to you to solve it numerically. In one of your projects, you actually will solve this equation for a general angle theta. The angle theta need not be small. You can have a large angle, even 90 degrees. You start off with a horizontal position of the pendulum. You can still solve for the angle theta. You can still solve this equation numerically to find the period. But I leave it to you in the project, not in the lesson. And what I want to find to do is to do approximation. If theta is given in radian, then for small angle, if the amplitude of oscillation is sufficiently small, sine theta can be approximated as theta, provided that theta is given in radian. And so the equation, I replace sine theta with theta, will become something like this. Now you immediately realize this is a simple harmonic motion because the second derivative of a quantity is equal to the quantity itself with a negative constant. And that is a property of simple harmonic motion, the standard equation for simple harmonic motion. And you can immediately write down the frequency because the frequency square corresponding to the coefficient that goes before the variable. And that is, in this case, G over L. So that means the angular frequency is G over L square root, okay? So the general solution, you also can copy the general solution, is given by A cosine omega naught t plus phi, where A is the amplitude, okay? That depends on, of course, and also phi depends on initial condition. For a particular case, if the bulb is released from rest at its highest position, when theta as t equals to 0 is equal to theta m, and theta dot is 0 initially, then we simply got the cosine term, okay, with amplitude equal to theta m, okay. Now you can find the period by using the period t equal to 2 pi over omega naught, and you will got the period as 2 pi square root alpha g. Okay, that is a period for a simple pendulum. Okay. Now, okay, the time is up, so we better stop here.